Swayam Prabha. Digital India. Educated India.
To this lecture series on foundations of cyber physical systems. So, in the last lecture we had been discussing this topic that is neural network based controller design for cyber physical systems, and with regard to that we started introducing ourselves to this issue of how to design a trained neural network, and we were discussing that why these update rules should be there, and if you recall, these are the update rules that we have been talking about. That suppose you have a multi-layer network, and in some mth layer you want to update the weights, the wij weights, and the bias bi from some value which is this in the to this. So, this is the value that has been updated in the kth step, and this is the value that will be updated in the k plus 1th step. And the idea was that there would be this gradient that is going to be computed, and this gradient would be multiplied by the learning rate, and then accordingly the weight and the bias is going to be updated. And in this context we also defined what is sensitivity of the loss function, which was like a derivative of the loss with respect to this value that is being computed n, right. So, basically we call it sensitivity because it tells that how much the loss is going to change with respect to the value that is being computed by the neural network. So, fine, let's move further on this. So, what we saw is that these derivatives can be expressed in a nicer form using this chain rule of differentiation, that you can write these derivatives in terms of the sensitivity. That means the first derivative here would be sensitivity times derivative of n with respect to derivative of weight, and given this formula relating n and the weights, it becomes sensitivity multiplied by this inputs itself of the m minus 1th stage. So, if you just draw a brief picture, okay. So, let us say you have this output coming from the m minus 1th layer, and this is the mth layer. So, the output that comes is a m minus 1. I am not writing the jth index or ith index those things, I am writing the thing as a whole. So, this goes and this gets multiplied with this weight here, right. So, this w gets multiplied with a, and then the bias gets added, and so that kind of is your n in the mth layer, right. And this would now, so this n would now go to the activation f, and this is going to generate this a m plus 1, the m plus 1th stage, right. So, in a way, if you take the derivative of this n with respect to the weights, you get the a values, right, which is the a m minus 1, and that is what you have. And if you take the derivative here of f with respect to b, and then you express it in terms of n, so then this first term becomes the sensitivity again, right, and this term is just 1 from this formula. So, overall you can write these update rules from the kth to the k plus 1th step using this, right. You have the update at k related with minus alpha sim, and in the kth step with the activation from the previous stage, right. And similarly, you can relate the value of bias in the k plus 1th step with the bias in the k plus kth step along with the learning rate multiplied by the sensitivity. So, overall if you are writing this in the vector form, then what you have is this expression would come in like this in the vector form, right. So, the overall weight matrix of the mth stage can be will have the k plus 1th update rate as per this, and the B matrix in the k plus 1th stage will have update as per this. And the other requirement, as you can see, so you have a refinement of both W and B happening for all the layers based on these values, I mean from the k to the k plus 1th state, right. So this thing can be done for the entire network, that's the point, right. So we can keep on computing for the entire network, that what is the mechanism using which the weight will be recomputed and the bias will be recomputed. You can do this for the entire network, right. But the next question that comes is, well, I am doing this, but how is this going to I mean, will there be any change again? So suppose I have already applied this thing. Now how again in the next step is the W or B going to change? The point is, well, with these rules that we have written, we have updates happening on the weights and the B value, but that's not the only thing. The other thing is the sensitivity value also needs an update. So what happens is we should be able to link up sensitivity value across layers, and let's do that here. So let's see that how the sensitivity value can be defined. So this was our definition of sensitivity, right. So this was our definition of sensitivity, and that means derivative of the loss with respect to the value that is computed. So express it in terms of A, and again you use the chain rule of differentiation. Now as you can see that then what you have is if you look at this next term which is A and M. So if you see N is acted on by the activation and produces A, right. So effectively Fm is the activation in the mth layer. We have this relation. So that would really mean, if I am doing this delta AIM delta that is actually a derivative of Fm NIM. So that's the derivative. So that's how this second term becomes this derivative. And what about this first term, derivative of F with respect to derivative of AIM? So let's try to write it in a different way. So you can write it like derivative of F with respect to derivative of N in the next stage. So why is that important? Let us try to understand. Again, let's understand how the different layers should be linked up. So you have the m minus 1th layer and you have the mth layer. So in the n minus 1th layer you have the output as sorry, let's try to link up mth and m plus 1th layer. That will be more relative with this expression that we have. So we have the mth layer and we have the m plus 1th layer. So that's kind of the sequence, right? So Nm acted upon by activation F gives you Am, then you have the weight of the m plus 1th layer to give you n of m plus 1, and then it's acted upon by the activation layer again, and you get the final value Am plus 1, right? So what we are saying is, well, we have the loss with respect to A in the mth state, which is this, but rather than that, let's express it in terms of this. We will see why. So instead of writing this, you can write del f del ni m plus 1, and then take a derivative of delta ni m plus 1 with respect to derivative of am, right? So effectively we want the derivative of f with respect to a, and then we express it in terms of the, because we want to link up the different layers, right? So we want to we take the derivative of f with respect to m plus 1th layer, and then take the derivative of n in the m plus 1th layer with respect to the derivative of a in the mth layer. Okay. So if you do that, what does it come out to be? So if you see, you have this relation between n's and w, right? So you have something like this, right? So if you take this derivative, you get this w, but this w is of the m plus 1th layer, right? So the second derivative, this term gives you this, and you still have the first term. But by the way, what is the first term? So if you see, this is just the definition of sensitivity for the m plus 1th layer, right? So then you have sensitivity of the m plus 1th layer multiplied by weight in the m plus 1th layer, its transpose, multiplied by the derivative of f, right, the activation. So overall, we can link up the mth layer and m plus 1th layer sensitivities like this, that Sm is nothing but the derivative of f multiplied by the transpose of Wm plus 1 multiplied by Sm plus 1. So that's how it is. That's how these sensitivities are going to be linked up across layers. But then what is the implication of this? So in effect, what we have is that we have update rules for the weights as well as an update rule for the sensitivity. So you need to have a method by which you initialize the weights, sensitivity value, and the bias, and there are well-known methods in neural network literature using which they are going to be initialized. You can study this material which I have cited here, and also the authors of the same material, they have a nice book on neural networks. You can study from there that there are well-known techniques of how to initialize these values. So that means if you initialize W0, S0 and B0, from there you can keep on computing these W values, their kth estimate and then k plus 1th estimate, like that, right? So right now, let's say you have some estimate of S here, the sensitivity, and you are using that estimate to compute using the current estimate of W, what is the next estimate of W, and from the current estimate of B, what is the next estimate of B. In that way, you move through what we call as a forward pass to the entire network, and you estimate these values of W's and B's. Okay. So once you have done that for the entire network, you will have newly computed values of W's and B's for the entire network. Now you see, so you have updated the W's, right? So once you have updated the W's, that means you have a change here. Once you have a change here, you use this change to recompute your sensitivities. That's the point. So that means now after this forward part, whatever earlier was your W and B, they have all changed. So you start from the last layer, okay, for which you have the sensitivity Sm known. So use Sm and this updated value of Wm to compute Sm minus 1, use Sm minus 1 and updated value of Wm minus 1 to compute Sm minus 2, like that, and this is what we call as a backward pass, and you go back and recompute all the sensitivity values. Okay. So that is like an update on the sensitivities. Once these sensitivity values are updated, you use these updated sensitivity values to recompute again in the forward pass, the next forward pass, further updates to happen on the W's and the biases. Use these updates on the biases and start with the last computed sensitivity value at the end and the last layer, and again use the backward pass to go back. So that's the back and forth computation, which is part of the backpropagation algorithm, and that's how the neural network will finally converge through to a position from where the loss function is not getting minimized anymore. So let's understand what's really is happening. Every time when you are recomputing the sensitivities, you are essentially refining your gradient. You are essentially refining your estimate of the loss function with respect to some position in the state space, and you are retuning your values of weights and you are trying to figure out what are the values of weights for which the loss function is going to be more minimized like that. So that's basically a gradient descent kind of technique through which you are making the loss function approach a minimum value. So there are well-known optimization theory literature on which you can find more details on this. Here we are just telling you that how this is kind of getting done more in a mechanical way. Fine. So we have an idea that well how the neural network training actually happens, and let's now figure out that well how we can really use these kind of trained neural networks in our context of cyber physical system design. So when we are doing this kind of CPS design, neural networks can be useful for their nature that they are very good at approximating some unknown functions. So if you look into this literature, you will see that they actually provide you a lot of interesting examples that how with different choices of weights and bias values you can make the neural network approximate a wide class of algebraic functions. Okay. So for any kind of unknown behavior with sufficient data that is gathered, sufficient training data that is gathered, it should be possible to create a neural network based representation of that unknown function. So this is what can be used to create an approximate model of a nonlinear system, and that's how it is used. Like it can be used to model unknown plant dynamics. Suppose there is a plant for which you want to design a controller, but the plant's model is unknown. So what one can do is one can give inputs to the plant and check what is the output coming from the unknown model, and one can also use this kind of data set to train an approximate neural network, and then you can keep on doing this, like you have the input and output, and you also have the predicted output from the neural network. So compare these two outputs to get the error function and retune the neural network to using some training algorithm, which we denote here by this adaptation block, where the training algorithm's objective is to keep on minimizing the error. So you have inputs, and based on that you have errors, and you ask the training algorithm that well for this neural network you optimize the weights more and more, so that with every iteration whatever the unknown function is outputting and whatever you are outputting, the neural network is outputting, the error must get minimized. Okay. So here whenever we talk about adaptation, we mean such a training method for which the objective is to minimize this error. Okay. This is kind of a very standard technique which is used for nonlinear system identification. You can see that in MATLAB there is a system identification toolbox using which this kind of methods can be automatically done. So you can model a plant dynamics using this, and you can learn the plant's dynamics, and not only that you can use this kind of technique to figure out that well for a plant, so that's about modeling a plant's dynamics. But not only that, you can also use neural network based approximations to create a controller model. We will talk about that more maybe in the next lecture. Thank you for your attention.